Hello, my name is Maisa and I'll be presenting time and frequency domain numerical analysis for electrical circuits under fixed large signal, stimulus, and variable small signal sources. Power system nonlinear devices are subjected to an input signal containing a strong fundamental component and much smaller harmonics in the amplitude due to voltage and current distortions in power grids. An analysis that aims to study the impacts of small signal harmonic injectance and its variation in a system results in a simulation with high reconfigurability. In this case of analysis, the circuit topology and the fundamental amplitude injected by the independent source are fixed, varying only the amplitude of harmonic components injected by the independent sources. Using traditional transient simulation, a new complete circuit analysis is required for each new harmonic component injected into the circuit by independent grid sources. The objective of this work is to discuss two different approaches that allow to perform such simulation in a computationally more efficient way. In the transient analysis, the solution of a circuit requires a series of analyses equally spaced in time to obtain the complete response of the circuit in a time interval. The solution depends directly on the initial conditions of the circuit. To analyze power system circuit, considering the amplitude of the harmonic components variation, when using traditional transient simulation, it is necessary to perform a complete analysis of the circuit at each new harmonic component injection value, making the process more computationally expensive. The superposition between large and small signal analysis involves the simulation of the complete nonlinear circuit initially considering only the large amplitude source. This first step is carried out through a periodic steady-state analysis. Then, the circuit is linearized around the steady-state response due to the source at the fundamental frequency, and only in this moment the small signal sources are injected into the circuit. The contribution of the harmonic injection sources are analyzed one at a time, always in a linear circuit. The system response is the superposition of the nonlinear large signal analysis and the small signal analysis in the linearized circuit, as expressed in this equation. The periodic alternating current method, or PAC, usually adopted for analysis of radio frequency electronic circuits, perform the superposition in the frequency domain with the help of the harmonic balance. In harmonic balance, each time varying unknown and equation are replaced by a set of 2 times h plus 1 constant unknowns and algebraic equations in the frequency domain, being h the number of harmonics to be considered in the simulation. By transforming all the characteristics equations of the circuit components, given in the time domain, to a set of equations independent of each other in the frequency domain, the steady-state response of a nonlinear circuit powered by a sinusoidal signal is represented by a vector of values corresponding to amplitudes of sine, cosine, and constant components, as presented in this equation. For nonlinear circuits, the frequency domain vector of amplitude is converted to the time domain, aiming to handle the nonlinear function in time domain. This linear transformation is provided by the F matrix as shown here. Also, a Jacobian matrix is created for the dynamic elements such as capacitors and inductors. The next equation represents an inductor characteristics equation transformation to frequency domain. L indicates the inductor inductance, VL and IL specify the vector inductor voltage and current respectively. In the linearization of the nonlinear components of the circuit, the derivative of nonlinear equation around the large signal response is performed, obtain a vector G with 2 times h plus 1 position. It consists of a conductance amplitudes multiplied by time domain functions of sines and cosines and fundamental frequency and their harmonics. From the vector D, it is possible to create D0 and D key as presented and then compose the conductance matrix count, which is used in linear frequency domain characteristics equation of nonlinear components. Lastly, for simulation with high reconfigurability in the amplitudes of harmonic sources without changing the rest of the circuits and the large signal sources, the PAC method is indicated. The shooting method is used for solving boundary and initial value problems. It is a numerical procedure based on time domain analysis. This method is valid for linear and nonlinear systems of algebraic equations in which the unknowns are the initial conditions. So, it can be used for solving linear and nonlinear electrical circuits. However, it is mandatory knowing the fundamental frequency of the current of voltage-independent sources, and the signal must be periodic in time. The set size of nonlinear algebraic equations in these methods does not depend on the number of harmonics injected in the electronic circuit. However, it is equal to the system order. Since the shooting method finds a solution that provides a steady-state condition for a circuit with dynamic elements, the final value of each state variable x, which can be capacitor's voltage or inductor currents, calculated after a period t of the fundamental frequency, is subtracted by the initially assigned value at t0, and they must be identical, as shown here. The final values are estimated by transient analysis. Therefore, the initial guess has a big influence on the convergence of the system solution. The differential equations presented in the circuit mathematical models are discretized and integrated at each time step. In general, it is necessary differentiation in the element equation in relation to an initial trajectory for linearizing it. For example, the linearization of an unknown is shown here, which x0 is the initial trajectory, f and l is the nonlinear function of the unknown x for being linearized. Thus, a first shooting method is applied in the nonlinear circuit being fed by large signal and fundamental independent source acting separately, and at the end of simulation, the function is linearized around the result. Thus, the signal becomes time-varying with the same frequency that the fundamental signal. Then, the shooting is applied in the linearized system being fed by one of the small signal sources. The process is repeated by each small signal source acting alone. The full response of the signal is given by the superposition of the response of each independent source by algebraic summing the results. The proposed approaches have been applied through arbitrary nonlinear dynamic circuit simulation. The case study consists of a saturable inductor that represents a passive nonlinear load. The voltage source Vs represents the system-independent power source at fundamental frequency, and the harmonic injected by other small signal external source is associated with Vp, and the voltage source association is described as the presented equation. The inductor current is equal to the time variable of the hyperbolic tangent of the inductor current expressing the nonlinear behavior. Considering only the presence of an independent voltage source in the circuit, that is, disregarding independent source that inject harmonics in the circuit, large signal simulations were developed. Subsequently, an independent source that injected a third harmonic into the circuit was included. It is possible to conclude that approaches in the time domain and the frequency domain have corresponding results in both cases. Aiming to verify the validities, both methods' response have been compared with the transient method. As seen in the second figure, they have converged. In order to present the injection of one more harmonic component in the system, an independent source was included in the 50th harmonic of the fundamental frequency of the circuit as presented. Also, in the second figure, we can observe the effectiveness of both approaches with the inclusion of the third and 50th harmonics in the system from the confrontation with the transient simulation. By developing the analysis, it was observed that the number of harmonics injected into the system is directly proportional to the number of unknowns in the PAC simulation. For shading method simulation, the shorter the time step, the greater the number of iterations needed to converge on a response. From the comparison between both approaches and the commonly used transient simulation, it can be concluded that both methods, generally implemented in radio frequency circuits, can be used in a nonlinear low-frequency dynamic circuits, such as those found in the power system. Considering their interactive process, they are more computationally efficient than transient, mainly for a serial inclusion of sources injecting harmonic in the circuit. Upon the method calculus and computer effort being compared, the number of unknowns is higher for PAC. However, the complexity of SM is increased because it demands for one fundamental period transient analysis. Thank you for watching.